Electricity is part of the world around you. Whether it appears as lightning or a spark inside the combustion chamber of an automobile, electricity can be found everywhere. Any room you enter is likely to have an outlet that provides access to electrical energy. In fact, electricity is such a common part of your environment, at times it may seem harmless. But electricity should never be taken for granted. As you work with electrical systems, you must never forget that electricity is dangerous. The danger isn't as obvious as the flames of a fire. Touch them and you know you'll get burned. But the fact is, even though you can't always see it, electricity can kill you. Working safely with electricity. Part 1. Electricity can kill. In this program, you'll see how the human body is affected when it receives an electrical shock. You'll also review what electricity is and how it flows in a circuit. Finding out what electricity is and how it can hurt you will let you develop ways to avoid being one of the thousands each year who are injured or killed because they forget that electricity is one of the most dangerous forces in nature. As an electrical current flows through a circuit, you can't actually see it, but you can observe its application as it powers the conveniences around you. Your television, your coffee maker, and your computer are all powered by electricity. As you use these tools, it's easy to forget that electrical energy is flowing through their circuits, enabling them to get the job done. Electricity, when it flows in a circuit, is useful and safe. This is because the wiring that carries current is designed to provide a path that is shielded from human contact. As long as electricity remains within that path, you're unlikely to get hurt by current. But under certain conditions, electricity can leave a circuit and flow elsewhere, including through your body. It is then that electrical energy can be deadly. Working safely with electricity means being aware of its danger and avoiding situations that place you at risk. To understand why electricity must be treated with respect, let's look at what happens to the human body when it receives an electric shock. An electric shock occurs with the passing of current through the body. As current flows through a part of the body, it can create a number of serious physical problems. The severity of these problems is determined by the amount of current, the path current takes through the body, and the duration of the shock. The first serious problem is a disruption of the body's internal electrical system. To better understand what this means, let's take a quick look at how electricity is used by the human body. Your brain exerts its control over movement by sending electrical signals to your muscles. If you extend your arm, let's say to connect a plug into an outlet, your muscles accomplish this task by reacting to electrical commands traveling from your brain, through your nervous system, to your arm. When an outside current flows through your body, perhaps from a faulty outlet, the external current can override the electrical signals of your nervous system and cause a loss of voluntary muscle control. In some cases, the external source of current is powerful enough to hold the victim in the circuit. The victim is not able to let go. When this happens, the victim is said to be froze on the circuit. Since electric shock injuries are more serious the longer current flows through the body, being froze on the circuit is extremely dangerous. If current is not cut, or the victim isn't forcibly removed from the circuit, injuries from the shock will be fatal. Even if an external current isn't strong enough to hold a victim in the circuit, it can indirectly cause serious injuries. This occurs when the body reacts to current by violently pulling away from its source. This is called a jerk reaction and is similar to what happens when someone touches a hot surface. Cuts, bruises, falls, and other accidents resulting from jerk reactions are among the most common types of injuries caused by low-current electric shock. For this reason, many safety experts recommend wearing leather gloves when you're working on any energized circuit. In this video, all circuits have been de-energized in advance so that gloves aren't necessary. Later, you'll be shown the proper way to de-energize a circuit. As the amount of current flowing through the body increases, the type of injury becomes more serious. In addition to lost muscle control, the flow of current burns body tissue. These burns are a result of the heat generated by the flow of current. The severity of injury received from an electric shock is also determined by the path of current through the body. For example, a current that flows in one hand and out the other passes directly through the chest. This path of current exposes the heart, lungs, and other vital organs to serious damage. Even a low current following this path could disrupt the electrical signals that control the beating of the heart. An electrical disruption of the heart is called fibrillation. Any fibrillation can be fatal.
We had a boiler tripping due to a loss of a large industrial fan called an induced draft fan. We went down to troubleshoot it, and we had removed the breaker, decided to investigate external to the breaker cubicle.
The switches in the previous manhole were marked wrong. So when they did, according to the prints, they did the wrong cable. And the development was turned back on. Instead of the one cable being off that I was to work on, it was energized by mistake. It was laying in the manhole at 7,000 volts energized, not touching anything.
And I went up into a phase port and contacted it. Fortunately, I was not grounded, or I would have immediately drawn a 4,000 volt shot through myself. But when I took the other probe and went up into C phase, as soon as I approached it, I generated what was known as a phase-to-phase fault, and which immediately tripped the feed breaker that fed that bus, that live bus. I was up into the live taps, incidentally, but it also created a blast.
The last thing I remember is I stepped down in the manhole.
So
after that, the flash occurred. I don't really exactly know what I did, whether I grabbed it, whether me stepping into the manhole caused the elbow to touch something and then start the flash. You know, the elbow, they said, apparently hit me in the arm. It went in my arm and out my leg.
So what I caught in my face and my body actually from the knees up, thighs and so forth, was a momentary fireball. And I also, where the probes were touching metal, it had melted the metal and so forth. So it's similar like being in it's as white as a welding arc, for example, and essentially that's really what it is. It's, you're right.
How badly you're injured depends on the strength of the current, the length of the shock, and the location of current flowing through the body. If you're going to be exposed to the hazards of electricity, you should have a basic understanding of how current flows and the factors that work together to increase or decrease its intensity. Let's look at the facts about electricity.
At its most basic level, electric current is the movement of subatomic charge carriers called electrons. Under certain conditions, electrons jump from atom to atom, creating a flow of current. The energy of this movement of electrons between atoms is electricity. But since everything is made up of atoms, why isn't electricity constantly flowing everywhere? Why aren't electrons always flowing from atom to atom? The answer lies in the attractive and repulsive forces of electrical charge. An electron is negatively charged. Two electrons repulse or push away from one another. Inside the atom is another particle called a proton, which is positively charged. A proton's positive charge pushes it away from other protons. But negative and positive charges are attracted to one another. The attraction between negatively charged electrons and positively charged protons helps hold an atom together. This is why current flow, the movement of electrons between atoms, is an unusual event. Normally, electrons are held inside atoms by their attraction to protons. Electrons will leave an atom only when they're exposed to a force more powerful than their natural attraction to protons. Current flows because electrons are influenced by a force called voltage. Voltage is also called a potential difference. This difference refers to a disparity between positive and negative charges. Voltage induces electrons to move between atoms by providing a greater positive attraction than the protons within the atom. Electrons are literally pulled out of atoms by their attraction to a greater positive force. Increasing voltage simply means providing a greater difference between positive and negative charges. Increasing voltage in a circuit means increasing the strength of the pull on electrons. A natural result of higher voltage is an increase in the number of electrons pulled through a circuit. The number of electrons traveling in a circuit is described as its amperage.
A high-voltage circuit is dangerous because it's capable of moving a large number of electrons through the circuit. But the degree of injury caused by a current is determined by the intensity of electron flow, or its amperage. But voltage and amperage alone do not determine the amount of current flowing in a circuit. How much current flows is always the result of the relationship between three characteristics of the circuit: its voltage, amperage, and its resistance.
Resistance is the opposition to the flow of current. Remember, current flow is unusual in nature because negatively charged electrons are held inside atoms by their attraction to positively charged protons.
It requires the introduction of an outside power source to move electrons from atom to atom. Some materials are made of atoms in which the electrons strongly resist flowing. These materials are described as having high resistance. All materials, even conductors, offer some resistance to the flow of current.
In any circuit, the amount of current flow can be determined by dividing voltage by resistance. The relationship between these three characteristics of a circuit is known as Ohm's law.
Now that you've seen the factors that determine how much current will flow in a circuit, let's use this information to see how much current will flow through the body. First, keep in mind that the human body isn't a natural conductor. It will generally resist the flow of current, but the amount of resistance offered by the body will vary.
In the past, the body's lowest resistance has been underestimated. Body resistance varies from about 500,000 ohms when dry to as low as 300 ohms when wet. When body resistance is low, a higher current will flow through the body. As a result, voltages as low as 30 volts can be fatal. Any circuit with a potential of 30 volts must be considered dangerous.
Remember, serious physical injuries, including loss of muscle control, internal burns, and even death, can occur when a low current flows through the body. This means that almost all sources of electricity are dangerous. To give you an idea of the effects of low current, let's look at some of the symptoms associated with current flowing through the body.
Currents just above 1 milliamp can cause a sensation. Between 1 and 8 milliamps, a clear sensation of current will be felt. Even at this point, the victim is nearing the froze on the circuit threshold. Now, as current approaches 10 milliamps, a victim may not be able to let go of the circuit. At currents between 20 to 100 milliamps, a victim can become paralyzed. This paralysis will prevent the lungs from taking in oxygen, and the victim may suffocate. Above 100 milliamps, fibrillation of the heart is almost certain. As current flow through the body rises above 200 milliamps, severe burns occur. In addition, there will be muscle contractions so strong that the heart, instead of beating out of rhythm, can actually stop.
In some cases, a victim will survive these currents, particularly when the length of the shock is very short. But since low currents can kill, following safety rules when working with electricity is vital. Now let's review the key segments of this program.
1. Working safely with electricity means being aware of its danger and avoiding situations that place you at risk. 2. Electrons flow in a given direction because they're influenced by a potential difference or voltage. This movement of electrons is commonly called current flow. 3. The severity of injury from an electric shock is determined by the amount of current flow, the length of the shock, and the path followed by the current. As little as 30 volts can be fatal. In the next program, you'll look at how to avoid getting injured by electricity